Here we have the power rule for derivatives, which is denoted as such. d dx, x to the nth power equals nx, the nth power minus 1. So the power rule helps us take the derivative of a variable that's raised to an exponent, right? So if you ever struggle to figure out where the power rule is applicable, there will always be a variable that's raised to an exponent. And our first step to solve the derivative is always to move the exponent down in front of the variable, which in this notation is the x right here. But if there's a coefficient, you multiply the power that you bring down by that coefficient. And the final step would be to subtract 1 from our original exponent. But let's work through some examples, as that typically solidifies how to use the rule correctly. Let's find the derivative of x to the 5th power. And remember, this is our formula right here. So in this scenario, the n, well, in every scenario, the n is always the exponent, right? Which in our example is the 5. So let's rewrite this knowing what our n value is. d dx x to the 5th power equals, okay, so we know our n equals 5. So all we have to do is plug this in anywhere we see an n. So we have an n right here, which will be 5, x, n to the 5th power minus 1, which would be 5x to the 4th power. So the derivative of x to the 5th power using the power rule is 5x to the 4th power. That's it. For this next example, we need to find the derivative of x squared. Okay, so remember, our first step is to figure out what the n is. The n will always be the power, which in this case is 2. So if n equals 2, let's just plug in 2 anywhere we see an n. So we have dx x squared equals 2x 2 minus 1, which would just simplify to 2x to the 1st power, but that's just 2x. So the derivative of x squared using the power rule, 2x. Okay, so what happens if we're asked to solve a derivative that has a coefficient in front of our variable? So what we're going to do is we're still going to use the power rule, but we also have to apply something that's called the constant multiple rule, which is written like this. d dx c, which is our constant, times f of x equals c times the derivative of f of x. So really all it's stating is that our coefficient has to be multiplied by the derivative right here. But let's work through some examples to make the image a bit more clear. Here we'll find the derivative of 7x cubed. So again, we have to find our n, which is the power that our variable is raised to, which is 3. So still, we are going to plug in a 3 anywhere we have an n. But we also have this coefficient of 7. So at the very end, when we have the derivative of x cubed, we're going to times that by the 7. So it's just an added step. So let's write down what that looks like. d dx 7x cubed. And we're just going to place that 7 right here, and we'll come back to it later. Then we're going to just plug this in. But we're going to use a 3 for our n. So 3x 3 minus 1, which should simplify to 7 times 3x squared. So then our final step is to multiply these two together, which would equal 21x squared. So the derivative of 7x cubed is 21x squared. And when there's a coefficient in front of our variable x, our final step is just to multiply them together. That's it. We'll work through one more example here. So let's try to find the derivative of 4x squared. So again, the n is just the power that our variable is raised to, which in this case is 2. And our coefficient is 4. So we'll write that as d dx 4x squared equals, remember we're just going to pull out our coefficient right here, we'll come back to it at the end, and then we'll have 2x 2 minus 1, which would just simplify to 4 times 2x. Our final step is to multiply our coefficient times the derivative, which would equal 8x. So the derivative of 4x squared is 8x. Okay, so what happens if we need to solve for the derivative of a constant number? Well, the power rule won't apply. Well, it can apply, you don't need to apply it because there won't be an exponent, but we will use the constant rule for derivatives, which is written like this: f prime of x equals 0. Incredibly simple. And all it states is that the derivative of any constant number, 7, 20, 100, 374, any constant number that's not attached to a variable or an exponent, it's just going to be 0. So let's work through an example to make that a bit clearer. Okay, here we have an example. Find the derivative of 19. There is no variable x attached. You don't see a visible exponent, so we're just going to apply our formula, f prime of x equals 0. So f prime of 19 just equals 0. The answer will always be 0. If you have just a constant number like 19, 12, 7, 100, 1000, whatever the number is, there's no variable attached, there's no exponent attached, the derivative is just going to be 0. But if you wanted to use the power rule, you could. You don't have to because the derivative of any constant is just going to be 0. But if you wanted to, it would look something like this. Okay, if we were to use the power rule to solve for the derivative of 19, it would look like this. We'd basically add this unseen variable x, and to that x we would attach an exponent of 0, which would work out to 0 times 19, 0 minus 1, which would simplify to 0 times 19 to the power of negative 1, which would equal 0. But you're probably asking, why do we add 0 as the exponent and not just 1? Well, I'll tell you. All constant numbers have an unseen exponent of 1. So for our example, 19 to the first power, it would just equal 19, right? So the number is unchanged. The value stays the same because the answer is just the base itself, right? But any number to the power of 0 will just equal 1. So 19 to the power of 0 equals 1. 200 to the power of 0 equals 1. 1000 to the power of 0 just equals 1. So knowing this, let's go back to our example and I'll explain a bit more why this all works out in the end. Okay, our original example was to find the derivative of 19. And this was our original formula, right? But when we're solving for 19, which is a constant, we're just going to plug it in like this. So d dx 19x, remember that unseen variable of x, and we're going to add an exponent of 0 to that x. Why? Well, because any power to the exponent of 0 is just going to be 1. So if x to the 0 power is 1 times 19 will still give us just 19, right? So if we apply our original formula and we bring that 0 down, it'll look like this. 0 times 19x, the original exponent 0 minus 1, which would simplify to 0 times 19x to the power of negative 1. But because we brought this 0 down right here, anything times 0 will just equal 0. See? So again, we're adding to our 19 an unseen variable of x, which has an exponent of 0. And from what we learned earlier, anything to the power of 0 is just 1. So this is why f prime of x equals 0. That's why that works, but you don't have to go through this entire work every single time. This is just why it works, but just remember that the derivative of a constant, it's always going to equal 0. So hopefully that helps, and if it doesn't, just remember that the derivative of a constant, it equals 0, and forget everything else. Okay, when we're working with the power rule, or just derivatives in general, there's one additional rule that you should know, which is that for derivatives with multiple terms, you can apply the sum and difference rule, which is denoted like this. d dx f of x plus or minus g of x equals f prime of x plus or minus g prime of x. That might sound complex, but all it means is that we can apply the power rule to every term and solve individually. It just simplifies things a bit more, but let's try an example so I can explain it a bit better. Okay, so here's our example. We're going to try to find the derivative of 4x cubed plus 2x squared plus 3x to the 6th power, right? So here we have term 1, term 2, and term 3. And all we're going to do is apply that derivative to every single term separately. So written, it would look like this. d dx for x cubed plus d dx 2x squared plus d dx 3x to the 6th power. We're just separating it into 3 parts. And remember, this right here is our original formula. So when we apply that individually to each term, it would look like this. For the first term, it would be 3 times 4x, 3 minus 1, plus 2 times 2x, 2 minus 1, plus 6 times 3x, 6 minus 1, which would just simplify, like if you times these two together, subtract that, it would be 12x squared. Do the same with this term, times 2 by 2, subtract 1, would just give us 4x, plus times 6 by 3, 6 minus 1, it would give us 18x to the 5th power. So we just applied the power rule individually to each term, which has helped us work through it a bit quicker. So the derivative of 4x cubed plus 2x squared plus 3x to the 6th power is 12x squared plus 4x plus 18x to the 5th power.